Fossil dinosaur bone, from biological structure to silicified stone. What we mean by fossil. A fossil is preserved evidence of ancient life with a geological record. Dinosaur fossils date from approximately 230 to 66 million years ago. Preservation may involve physical remains or behavioral traces. Most dinosaur bone specimens are fully mineralized stone, not original bone material. Why fossil dinosaur bone is rare. Organic remains normally decay or are scavenged. Fossil requires rapid burial, stable sedimentary environments, mineral-rich groundwater. Only a very small percentage of dinosaurs entered the fossil record. Initial conditions for fossilization. Death. Dinosaur dies near water, floodplains, deserts, or volcanic regions. Rapid burial. Mud, sand, or ash covers the remains quickly. This prevents scavenging and decay. Mineral-rich groundwater carries dissolved minerals flows through the buried bones. Permineralization, minerals fill tiny pores in the bone and slowly replace the original material. Stone bone. Over thousands to millions of years, the bone becomes rock. Exposure. Erosion and tectonic activity eventually reveal the fossil. Permineralization is the dominant process. Groundwater migrates through buried skeletal materials. Dissolved minerals enter microscopic pore spaces in the bone. Original organic material is gradually replaced. Bone morphology and microstructure are retained. Key process, permineralization. Geological timescale of fossilization. Mineral replacement occurs over thousands to millions of years. Most dinosaur bone fossils represent multiple mineralization phases. Fossils are often younger than the surrounding host rock due to this reworking. What actually replaces dinosaur bone? Dinosaur bone is highly porous, ideal for mineral infiltration. Replacement minerals reflect groundwater chemistry, surrounding lithology, oxidation conditions. Color and patterns are mineralogical and not biological. Silica quartz group, most common. Dominant replacement mineral in dinosaur bone. Highly stable and chemically resistant. Hardness scale on the Mohs scale is 7. Preserve Austin's vascular canals and growth structures. Jasper replaced dinosaur bone. Would be opaque, colorful form of silica quartz. Colors will be caused by iron and trace elements. Common colors red, brown, yellow, and even green. Very common in dinosaur bone from floodplains and volcanic regions. Red dinosaur bone is usually iron-rich jasper. Agatized dinosaur bone. Translucent banded chalcedony forms through layered silica deposition. Exceptional preservation of internal bone structure. Highly valued by collectors and lapidary artists. Chalcedony replacement. Microcrystalline quartz. Parent material for agate and jasper. Most common replacement by volume. Often underappreciated due to the muted exterior appearance. Iron mineral overprinting. Hematite and goethite commonly present. Responsible for red, orange, and brown coloration. May partially replace and stain earlier silica phases. Indicates oxidation of the groundwater conditions. Calcite replacement occurs in carbonate-rich sedimentary systems. Softer minerals, Mohs 3, may replace bone or fill voids, less resistant to weathering and erosion. Pyritized dinosaur bone, rare to see. Iron sulfide replacement, forms under anoxic conditions. Metallic gold appearance, structurally unstable if exposed to oxygen and humidity. Host rocks that preserve dinosaurs. Fossils. Fossil dinosaur bone is found almost exclusively in sedimentary rock. Igneous and metamorphic processes destroy bone structure. Common fossil-bearing sedimentary rocks, sandstone, bones, and trackways. Shale, fine-grained detail preservation, mudstone, most common dinosaur bone host, and limestone, excellent preservation in select environments. Categories of dinosaur fossils. You have body fossils, mineralized skeletal material, and trace fossils, evidence of biological activity. Body fossils, bones, teeth, claws, skull fragments, dermal armor, reveal anatomy, size, taxonomy, and growth patterns. Trace fossils, trackways and footprints, nesting sites and eggs, coprolites, dinosaur poo, feeding traces. They reveal behavior, locomotion, diet, and social structure. Visual identification without any equipment. Possible observations: body fossils versus trace fossils, bone type and orientation, replacement minerals, jasper, agates, chalcedonies, oxidation patterns. Limitations apply for a visual representation. Whereas what requires laboratory analysis? Well, species level identification, growth stage determination, bone histology, and precise age of the fossil. Why dinosaur identification is complex. Many dinosaurs have very similar bones. Fossils are often fragmentary. Diagnostic features may be microscopic. Identification relies on global comparative collections. Amazing fossil facts. Dinosaur fossils exist on every continent. Most famous dinosaurs are known from partial skeletons. Some fossils preserve skin impressions, and many dinosaurs had feathers. Fossil poop reveals diet and ecosystems. Key terminology for collectors: fossil, permineralization, chalcedony, and jasper. The key takeaways for rock and gem enthusiasts: dinosaur bones become stone. Jasper, agate, chalcedony, and quartz are the most common replacements. Color depends on minerals, not dinosaurs. Sedimentary rock preserves fossils best. Body fossils show anatomy. Trace fossils show behavior. Naked eye observations gives clues where science can give certainty. Thanks all for listening today.